be teaching you about Boolean algebra and logic gates. So, first activity I would like to give you guys is, could you name the following symbols and provide sort of the Boolean algebra symbol for it. So pause the video and do it. Okay, so let's start with this one. This is a NOR gate, right? NOR, and the symbol for it is this. It's a weird 7, a funky 7. What about this one? This is an AND gate, right? An AND gate. If for this one, if this is true for the outcome, this outcome is equal to of the multiplication of these two. So if this is 1, this is 0, this will give you 0. And if this is 0 and this is 0, this gives you 0. Only when both are 1, it gives you 1. This will come into play later. Also, I did skip that for a NOR gate. This is just the opposite of the input. So the symbol for an AND gate is this. In maths, you may see it as this, but that's maths. That's different. Right, what about this one? That's an OR gate, and the symbol for it is this. What about this one? Well, this is an exclusive OR. It's similar to an OR, but it's exclusive. This means that it's the same as OR, but if the inputs are the same, then the output is always 0. The symbol for it is this. What about this one? Similar to an AND, isn't it? Well, for that, however, it has this nipple right here. That's what it's called logically, so don't think it's something funny. It's called the NAND gate. NAND gate. And it doesn't have any symbol, so how you would represent it logically would be like this. So x and y, well, this is x and this is y. X and y, not x and y. And this, again, the nipple, and it's the same as the OR gate, but with a nipple. It's a NOR gate, and the representation is the exact same. X or y, not x or y. Now, why did I put some word bracket here? Well, the explanation for it is that NAND and NOR are universal gates. What does that mean? A universal gate means that these two gates can be used to make all the other gates. So all of these gates, all of these gates can be made by combining several of these. In the exam, you don't need to know how to make a NOR gate from a NAND gate or an XOR gate from a NAND gate or whatever, but you do need to know that they're universal gates. Now, I want you guys to complete the following truth table. So pause the video and complete the following truth table based off of the symbols that we've learned here, right? Right, so recognize what the output is. The output is a NOR. So if A is equal to 1, not A is equal to 0. If A is equal to 0, not A is equal to 1. Now, what about this one for B? We'll realize what the output is. The output here is an AND, and the output there is a NAND. Right, I put this as an extension, but generally, AND gate, what is the logic? If A is equal to 0 and B equals 0, 0 and 0 gives you 0. 1 and 0 gives you 0. 0 and 1, that's still 0. 1 and 1 is 1. Not of that, if you realize this here is the same as this. It's just knotted, so it's the complete opposite. It's the NOR of it. So it's 1, 1, 1, 0. Now, the same with NOR. I mean, with OR and NOR, right? So below, you can pause and complete it. Right, so 0 or 0 will give you 0. Think of it as 0 being false and 1's being true. False or false will give you false. True or false, or either one of them is going to be true, right? False or true, well, it's true. True or true, it's true. And this is the opposite. Well, if this is false and this is false, if this is true and this is true, then the output is true. But if one of them is false, or both of them are false, then the output is false, as you can see below. So that's generally how the logic gates work. These can be then combined into different arrangements. So you can have the following of this. Now you see the output Q has a complex nature because it uses 2 logic gates. So for that, we represent it in Boolean algebra, where we combine the symbols. Now, Boolean algebra is kind of similar to regular maths, right? So in the exam, when you're giving the following, consider this, right? So make a note on this. So not of A is equal to 1 minus A. A or B is the same as A plus B. A and B is the same as A times B. See how I said before that the AND gate is just multiplication? Well, the OR gate is addition, right? So this multiplication, this is addition. So therefore, we can actually apply the logic into it. However, you need to know as well that when you get A or A, or A and A, you get A as a result. But I mean, if A plus A, which is equal to 2A, right, that gives you A. That's the same as A. Because the output is binary, is a 2-state. You can't have 2 in binary. It's A. That's wrong. It's either 1 or 0 in binary. So if 1 plus 1 gives you 1, 0 plus 0 is equal to 0. So that's why 2A is equal to A. And A squared equals A. A or 1 is always 1, right? Because if A is 0 or 1, you're still going to have an output of 1. A and 1 is A, which makes sense because A plus 1 is 1, but A times 1 is A, clearly. You also have to remember De Morgan's rules, which these help when simplifying algebraic expressions. So remember these 3 things, this and that, and these 2 things, and then you can do it. So now I want you guys to practice this question 1, right? Right, pause and answer the question. All right, first thing to do is to write it algebraically. A plus, well, actually, now, first thing to do is to realize that this expression and this expression are the same, right? So A plus C times A plus C, or C plus A and whatever. But because these 2 are the same, it doesn't really matter. And what is this equal to? A plus C times A plus C. That's the same as A plus C all squared. So now we have a squared. What to say about a value being squared is the same as the value itself. So A plus C squared, we have A plus C. And in the exam you have to write it algebraically, so it's A or C. And that's the finalized expression. That is the final answer. That's how you simplify it. Right, now, this question 2, pause it and give it a go. So, not A. So we have not A, and not B, and A or C. Now, before I do mine, so I personally like to keep the nots. I don't want to like put it mathematically yet. Only once I'm at a stage where I can't simplify any further, do I put it mathematically, right? So I like to write it as not A times not B times A plus C. Now, if we can rewrite that as not B times not A plus not A C times C, not A times A plus not A times C. So I just multiplied this into the brackets, right? Then we can simplify the knots. So 1 minus B times 1 minus A times A plus 1 minus A times C, which that gives you 1 minus B times A minus A squared plus 1 minus A C. Now A minus A squared, that's just the same as A minus A, which is equal to 0. Now that just leaves us 1 minus B times 1 minus A times C, which is the same as not B and not A and C, which is the finalized expression. Now, okay, so question 3. Now you're gonna think that this is a bit difficult, but it's not. It is not. B times 1 minus B times A times B plus A times C. Now we know that when you have a value times the knot of that value, it gives you 0. So we know that this is 0, this expression. So the same as 0 times A times B plus A times C. And that's just 0 times anything is 0, so that's just A times C, which is equal to A and C. That is our final value. Now question 4. Pause and give it a go. Okay, so that's just A times C plus, you see, recognize that this is De Morgan's expression, right? Not A plus not B. So how do we do this one? Oh yeah, my bad, I meant A times B. My bad. As a matter of fact, actually now I realize why I went wrong. It's actually A times C and A times B plus 1 minus A times B. We could have done it the other way, but this is way simpler. So it's the same as AB plus 1 minus AB. You can cancel the AB's out, so you have 1. And that is the final answer. You could have done it the other way, but it would just be way too complicated. Okay. 5. Now, this is De Morgan's scenario. In here, you could have used De Morgan's, but it wouldn't. But that you don't really need to do it when you have AB and AB here, right? But in here it's different because you have 3 different variables. So now you apply De Morgan's in this case. So you have, so before changing it algebraically, you have x and not y, or not of not y, or not z, right? And look, you know the De Morgan's, so we have x and not y, or y and z. Now we can change it to algebraic expressions. You have x times 1 minus y plus zy. And that is, and once we consider the actual expression, now when we try to simplify this, we won't be able to. So that means that this is in its simplest form. So in reality, the answer is x and not y, or z and y, which that is the final expression. Now that's pretty much all you need to know, and I will show you this. Question 6. This is a challenge. Try to do this one and put in the comments what the answer to it is. However, this won't be in the exam, so don't worry. But this is just another simple one. It's just a simple Boolean algebra problem, so it's easy to do. It won't be that complicated. But yeah, just make sure to do this one. And yeah, I've got to leave the easiest for last. So yeah, try it. Make sure to subscribe and like for more content. Bye bye.